Look at those alum crystals.
It's time for the weekly update on our alum crystals. As you can see in these vials, there are now many crystals, ranging from about 6 to 8 in each vial, and each of the crystals, while varied in size, ranges from about 3 to 6 millimeters. You can see that they are cubic in shape, meaning they look like little boxes. Also, they're transparent. There are many different environmental factors which could have affected the growth of these crystals, the main one being the random increase in temperature. This could have increased the rate of evaporation, increasing the rate of growth. Another possible effect could be increase or decrease in humidity. Just keep looking at the crystals. They're cute, aren't they?
If one would like to create one high-quality crystal, they would create a solution which is saturated with alum, in the same way that we created a solution for this project. However, just leaving a saturated solution to slowly evaporate creates many crystals, as seen in my personal vial. This can be changed by suspending a seed crystal within the solution. If there is a seed crystal, upon evaporation, the alum within the solution will attach to the seed crystal when it solidifies instead of forming crystals on the bottom of the vial. This is because of the attractive forces between the seed crystal and the alum within the solution.
Crystals form pretty, geometric shapes because of the internal arrangement of their molecules. A crystal is organized with different layers of atoms, each of which lay, one on top of the other, in a structured, organized arrangement. D-spacing is a phenomenon which refers to the distance between each layer of these molecules. The distance between layers of the crystals varies between different lattices. These different amounts of space between layers are important because they give the different crystals different properties, giving them varied uses. Furthermore, the D-spacing of each crystal is a unique signature. Using techniques like X-ray diffraction, one can find the distance between layers of the crystals, helping them to identify different materials.
One can find the D-spacing of the most intense peak on the given X-ray diffraction chart by using Bragg's law. This formula says that an order constant times the wavelength is equal to 2 times the distance between the layers times the sine of the angle at which the peak is taken. For the most intense peak on this diagram, the angle is 10 degrees. The wavelength, which is given, is 0.154 nanometers. The order of the peak is 4. This found by counting each large peak on the chart from the right. The most intense peak is the 4th from the right, so the order should be 4. When these numbers are plugged into the equation, one sees that D is 1.77 nanometers.